Hello, it is Wednesday, March 23rd, and we are going to be doing homework 4 today. So homework 4, we're going to illustrate how the CSTR can exhibit nonlinear dynamic behavior. We will simulate the effect of a step change in the coolant temperature in positive and negative directions. And we will derive some equations. We're going to manipulate the temperatures and the variable temperature in the water jacket, which is the coolant, which is what's cooling the system. And the two cases we're going to simulate, we're going to increase the temperature or decrease the temperature from 300 to 290, and then increase the temperature from 300 to 305 degrees Kelvin. Okay, so first off, you might be asking, what is a CSTR? A CSTR is a continuously stirred tank reactor. That means, since it's continuously stirred, that means the concentration, stop it, there we go. The concentration inside the tank is equal to the concentration of the flow leaving the tank. That will be important later. Okay, so let's make a quick diagram of what we're working with here. I can stay on red. So it said we have a tank that is continuously stirred. There's our stir. I'll make it a little deeper. A little stirry there. We have flow coming in, and then flow going out. We have a cooling jacket. With flow coming in and flow exiting. Now let's see if we have some variables for those things. So we can see already that at the initial temperature of the coolant is 300 degrees Celsius. Kelvin. We can see that the temperature inside the tank is 350 degrees Kelvin. Oh my lordy. Struggling. What else can we see? We can see that our flow rate going into the tank is 100 liters per minute, and our concentration inside the tank, going into the tank inside the tank, is 1 mole per liter. 100 per minute. And then that means our concentration is 1, what was that? Mole per liter. Now, since our flow rate is constant, that means that flow rate in is equal to flow rate out, which is equal just to the flow rate being constant, but that also means that our volume will be constant. And our volume is 100 liters. That is constant. Our next variable here is the density. That is also a constant at 1,000 gallons per liter. Okay, what else can we do with our diagram here? I think that is good for the diagram. Let's look at some more variables. So we said this was the flow rate. This is the concentration going in. This is the temperature inside. This is the volume. It is constant. This is the density. It is constant. This is the, what is big C? I remember. It is the, we'll come back to C once I remember. This is the enthalpy of the reaction. And we can see that it is negative because this is an exothermic reaction. I'm just going to make sure I'm recording. Okay, I am. Okay. Up here, these two variables, ER and K naught, if we do a little equation, we can figure out the reaction rate, which is, come off to the side, equal to ER over temperature. You can see we have our initial conditions right here. That was really bad. For our temperature of the coolant, the concentration of A, and the temperature inside the tank. U of A is the constant for heat transfer between the tank and the cooling jacket. Between the tank minus the cooling jacket. Back to C. What is C? C is it relates to energy, obviously because we have joules per gram of Kelvin. Oh, good gravy. Anyways, we'll come back to C. I'm gonna remember it, I swear. And then since the constant of heat transfer is between the tank and the cooling jacket, we can just figure that out real quick. That's just going to be U of A is equal to T minus Tc. So there we go. So the first thing we want to do is we need to figure out the concentration and the temperature. These are our two variables. So let's work on concentration first. So the rate of change of the concentration of A, which is dependent on volume, over, or with respect to time, is equal to flow in minus flow out, but they are the same thing. So Q times the concentration inside minus the concentration going out. But since we had a CRST, we know that the concentration in is the same as the concentration going out, so we can just put the normal concentration. I need to really make that small. There we go. So there's that. And then minus the reaction rate, which is K, times the concentration of A times the volume. But since volume is a constant, we can get it out of the right hand side here, multiply it out or divide it out, which would leave us with the flow rate over V times concentration of A going in minus concentration of A minus flow rate times concentration of A. That is a horrible V. So just like that, we have our concentration, our derivative, not our derivative, our equation to solve for the concentration of A. So now we need to solve for the reactor temperature. Now in order to do that, we need to look at the energy of the inside of the system. The only thing that is relating to the energy on the inside of the system is the temperature. But however, we have C. Now what is C? C is good golly. It's not specific heat. Heat capacity. C is the heat capacity. C is the heat capacity constant. Now in order to get the heat capacity of all of the fluid inside the system, that is C of the system, C system, would be equal to the volume times the density times C. Bam. Now if we multiply that by the rate of change of the temperature with respect to time, this is giving us, why can't I draw these? This is giving us the change in energy of the entire system, of the entire inside of the reactor. So this is the change in energy of inside of the reactor. Sing the song. Alright, here we go. That is then equal to the enthalpy inside minus the enthalpy outside, and then you also have to add the transfer of heat between the inside and the outside, or the cooling. So that is, where is it? We had it right here. U of A is T minus Tc. So how do we make sense of this? Well, magic. No, I'm just kidding. We can simplify that down into Q, the flow rate times the volume times the density is equal to the temperature inside minus the temperature going in minus the temperature inside of the tank, plus we're going to have, what was it, the rate of the reaction, yes, times Ca times the volume. But then we also cannot forget about the energy produced by the reaction, the enthalpy of the reaction. Just like that. Okay, so now we're here. Okay, let me write it out again just to make it look nice. Okay, so now we can divide VPC, or the volume, density, and and the heat capacity constant. I don't know why I can't remember that. To the other side, so we can get the rate of change of temperature with respect to time by itself. So let's see that. It's gonna net us Q and minus temperature plus, oh, I almost forgot something up here. Could have UA up here. Plus K times CA over PC and plus UA T minus TC BPC. It's actually rho. I just can't draw a rho, so I just draw P's instead. Gets the point across. Alright. This is not right. This needs to be Q over V, so that means I did this wrong up here. This is this way. There we go. So now we have our two equations to solve for our two variables. Kirchhoff.